Welcome to IVA Education, where we approach learning through understanding. Today's section is about projectile motion, which is the third part of Unit 2, Motion in Two Dimensions. In this section, we're going to cover free fall and projectiles. We'll study projectiles according to the two components of motion on the horizontal and the vertical. Then we're going to go to particular physical quantities related to projectiles, which are the highest point and the range. Before we start, we'd like to advise you and recommend that you sit and take the pre-assessment before starting this section. Then, throughout the session, if you'd like to pause or rewind and check any idea, go ahead and do it. Starting with a simple idea extracted from our daily life. Basketball, like most other sports, relies on the player's fitness in the first place. It also needs some physics there. In this section, we focus on projectile motion, which is of major importance in such sports. Free fall and projectiles. An object is said to be in free fall when it is left to move under the action of gravitational force. When the object is launched with some initial velocity, then left to move under the effect of its weight, it is said to be a projectile. Air resistance affects the motion of a projectile. However, at this level of studying, it is ignored to make calculations simpler. Some examples about free falls or projectile motion are launching a missile, playing basketball or just throwing a ball left under the action of gravity, and dropping a bomb. How are projectiles studied? In other words, decomposing projectile motion into two components. Since the projectile is acted on by weight only, then it experiences a downward vertical pull all the time. On the other hand, its motion is not affected by anything on the horizontal level. Checking this figure here, a projectile is launched from point, here it is O. Throughout all its motion, it's acted on by weight all the time, which is vertically downward. This produces a parabolic path of the projectile. The path followed by a projectile is called its trajectory, and it is parabolic in all the cases of projectiles. Having this in mind, we study projectiles in a remarkable way. Its motion can be decomposed into two independent motions. The first is motion on the x-axis or the horizontal line, which is uniform motion with no acceleration, and motion on the vertical, which is uniformly varied with an acceleration equal to that of gravity. You all know G equals 9.8 meters per second square, directed vertically downwards. Having this in mind, the first thing we do in studying projectiles is to set a reference frame OIJ, O being the origin, which is usually the starting point, I is the unit vector on the horizontal axis, which is usually called x, and j is the unit vector on the vertical y-axis. Checking this figure here, you have v0, the launching velocity at a certain angle, the I-axis or I unit vector, and the j unit vector on the x-axis and y-axis respectively. Second thing we start with is to set the initial conditions. The coordinates of the initial position r0, which are x0 abscissa and y0, and also of major importance is the initial velocity. We decompose it into two components, v0x and v0y. Usually v0x is v0 cosine alpha and v0y is v0 sine alpha. If you have any problems with projection, pause the video now and go to previous sections where we have covered projection of and decomposition of vectors. Some other particular cases of launching a projectile are horizontal launch and inclined launch downwards. Now, horizontal launch is important. Inclined downwards launch isn't of great importance. What's the difference between these two? In horizontal launch, the initial velocity has only one component, which is on x-axis, on the horizontal, while its v0 on y is 0. On the other hand, the inclined downwards launch has something important, which is its initial speed on y is minus V0 sine alpha. Now, studying these motions in details, as we said, we're gonna decompose our work into two parts. Motion on the x-axis, which is uniform with no acceleration, or a on x is 0. You'll notice that we use ax and ay to distinguish between x-axis motion and motion on y-axis. Here we use the boldface and the italics just for the highlighting of a certain equation. So we can use convenient time equations on x-axis. Vx is v0x, which is v0 cosine alpha in the general case. And if you go to position x equals vx times t plus x0, this is a characteristic of uniform motion. Thus x is v0 cosine alpha t plus x0, or better use delta x, which is the change in position on x-axis, equals v0 cosine alpha times t. A remark, it's always better to use delta x because it doesn't require any specifications concerning x0. It makes it a good choice to use. On the other hand, motion on y-axis is uniformly varied under the effect of gravitational acceleration. Thus, ay is equal to g directed downwards. And since it is a convention, or a sort of a convention, to choose vertically upward as positive, then ay is minus g. Thus, using convenient time equations for uniformly varied rectilinear motion on y-axis, vy equals at plus v0, and here we add the index y to indicate that this equation of motion is used on the y-axis. Thus, vy becomes minus gt plus v0 sine alpha. And y equals half at squared plus v0t plus y0, becoming minus g over 2t squared plus v0 sine alpha t plus y0. Again and again, if we consider delta y, this is of major importance, it becomes minus g over 2t squared plus v0 sine alpha times t. So as we said before, using delta y is better than using delta x. In addition to the above two equations, the first about velocity, this one, which is, let's call it 1, and this one, which we'll call it 2, we have the time-independent equation, which can only be used on the y-axis. So vy squared minus v0y squared equals 2 delta y times ay. Definitely you know that ay is minus g and v0y is v0 sine alpha. Now, if you have any problems remembering these equations, 1, 2, and let's say 3, go back to Unit 1, Section 3, if I'm not mistaken, where we discussed time equations of the different types of motion. A remark concerning delta y, it's always better to use delta y rather than using y alone, because when you use y, you have to worry about y and y0, the initial position. Delta y is simply considering the change in the y level or the height. Particular physical quantities related to projectiles. In order to discuss these two important points, which are the highest point and the range, pause a bit, go back to the previous equations, and try to memorize them. It is useful. First, we start with the highest point. The highest point is reached when the projectile stops elevating. Pay attention, it stops elevating. It stops moving on the y-axis only. It will keep on moving on the x-axis. That is when Vy is 0. So if we consider it in the projectile path, the particle is launched initially. As it elevates, you notice Vx is always the same, but Vy decreases until it becomes 0 on the highest point. Now, the projectile doesn't stop here, as you can notice in some cartoons. If it stops, it would drop directly here. No, it continues moving because it has some speed on x-axis, and it's going to proceed moving forward and falling down. The change between, or the difference between rising and moving down, is that Vy, which was directed upwards in the ascent, is now directed downwards as the projectile moves down. How can we achieve and calculate the highest point? The key is using Vy being 0. Solving Vy equals 0 minus gt plus v0 sine alpha equals to 0. So time t is v0 sine alpha. Usually v0, alpha, and g are given. If not, maybe one of them is going to be the target of a certain question. Substitute in y. Now, y in y, not in x, because simply we need the height. And the height is this level, which is parallel to the y-axis. Now, substituting in y, we get y equals minus g over 2. Let me erase this. Multiplied by the value of t plus v0 sine alpha multiplied by the same expression of t, and we get the final result. The maximum height is h equals v0 square sine square alpha over 2g. It's a simple calculation. If you'd like to go over it and you have any questions about it, don't hesitate to type it in the questions and answers part. Now, h equals v0 sine square or v0 square sine square alpha over 2g can be used directly whenever the highest point is involved. But keep in mind that this highest point is above the launching level, which is here the x-axis. X-axis might be ground level or it might be another level. So pay good attention to what the question demands, whether it is with respect to the chosen x or with respect to another direction or reference. A second useful particular quantity in projectiles is the range. What is a range first? The range of a projectile is the horizontal distance it covers as it falls back to its launching level. It starts at the level of y equal to 0 and it falls back to y equal to 0. Now, this might not be the end of the world. The projectile might continue downwards for some reason. But we say range when the projectile reaches the same launching level. In order to calculate the range, which is an x value if you noticed, we start by y equal to 0 as our call here. We solve it. We have an equation with two unknowns. We just solve for these unknowns. When a product of two numbers is 0, that means one of these might be 0. So first, t equals to 0, which corresponds to the launch point, so we're going to ignore it. Or, if you solve this equation here, equals to 0, you get t equals 2 v0 sine alpha over g. Now this time corresponds to the range time. In fact, this time corresponds to the duration where the projectile was airborne. We can call it the time of flight or the duration of flight. Taking this time and substituting it in x, you get x or r as in range, v0 cosine alpha times t, and t is 2 v0 sine alpha, and we have this result. So the range is 2 v0 square cosine alpha times sine alpha over g. Pretty interesting equation. Again, just like we talked about the height, it's important to memorize this. In questions, you can use it directly without referring to how it was developed in the first place. Now, summing things up, things related to projectile motion, let's have this simple cheat sheet. We always start any projectile problem by stating the initial conditions. Keep that in mind. And if not given, draw a clarifying figure where you can represent the x-axis, the y-axis, and mainly the launch velocity. Then, the x and y components are known to be independent, so we use directly the following equations. On x-axis, we have delta x being v0 cosine alpha times t, and vx is v0 cosine alpha. On y, we have these three equations. I'm not going to go into them. You can simply just memorize these equations to use them directly on spot. Two important particular expressions are the range, which is the maximum distance on the horizontal axis, which is indicated here as r, and it's given by the relation 2v0 squared cosine alpha sine alpha over g, and the highest point, which is the maximum value of y, or on the y-axis, which is v0 squared sine square alpha over 2g. Any other question related to projectiles should start by understanding what the question demands and then picking up one of these equations, either on x or on y, in order to solve. You don't need anything else to solve any problem related to projectiles. This is all concerning projectile and the equations that we need to use. You can write these equations on a piece of paper as we go now and solve an application about golf. You know the sport of golf. Before we do that, let's watch this amazing shot done by the famous golf player Tiger Woods.
He's chasing after this one. He likes it.
He said, come on, come on.
Oh, he should. How about that?
A golf ball shot with an initial angle of 34 degrees lands exactly 240 meters down the range on a level course. On a level course, meaning it's on the same horizontal line. Neglecting air friction or air resistance, what initial speed would achieve this result? Using the speed determined in term A, find the maximum height reached by the ball. Let's go to the solution. So first of all, reaching ground 240 meters away, this is an indication about which term? The range. So delta y is 0 and delta x is 240 meters, which is simply the range as we said. Now, using the equation of the range, which you have just written on a paper as we said, r equals 2v0 square cosine alpha sine alpha over g. Replace values. We have alpha 34 degrees. Now we know that g is 9.8. Whenever it's not given, you can directly use it. And the range is given to be 240 meters and the unit is acceptable. So just jot in the values, solve that equation. V0 squared is 2537.2, square root of the answer, and we get around 50.4 meters per second. That's it. The second question, using the speed we determined, let's find the maximum height. Again, if you check the paper that you have right now, the cheat sheet I mean, you have an equation for the maximum height. That equation is h equals v0 square sine square alpha over 2g. Replace values and voila, here you get the height, which is 40.5 meters above the ground level. This is an application about projectiles and how equations of projectiles are used. I hope you got it properly. That's all concerning this session. Thank you for your time. I would highly recommend that you go and solve the post-assessment, keeping the cheat sheet with you, check your understanding, then go do some reinforcement by solving some exercises from the worksheet assigned to this subsection, and you can also find the solution on the platform. At the end, if you need some extra information, go check our resource library for extra learning nuggets. Again, thank you for your time.